This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. So in the last lecture, we studied the chapter of the gas turbine cycles, and there we discussed that gas turbine is one type of combustion engines. So let's say a few words about the different types of combustion engine. So to have a general idea in terms of how this gas turbine compared to other types of engines that is available out there. So first we mentioned that combustion engine is basically the device which is convert chemical energy stored in the fuel and then deliver the mechanical work as the useful output, right? And this process using intermediate form of energy, which is a thermal, or if you have talking about the process from a system to a surroundings, then it's in terms of heat, right? But this part doesn't have to going through this thermal energy step. And we mentioned that there is other ways can realize this process. That's called can be called as electrical propulsion. So electrical propulsion, actually, if you compare these two, they have the same input and same output. Input is the fuel chemical energy, and same output, which is mechanical work to drive a car or drive some other devices, right? But they're using different energy form in terms of the in the middle. So this one using thermal energy, and this one using electric or electricity as the energy in the middle. Because this one is not evolving heat, it's not limited by the second law. The second law is essentially being designed or being discovered for the heat engine, where you're using the thermal energy as an intermediate energy form. if you're using electricity, you are not limited by the second law. So in other words, you are not limited by the kernel efficiency. But why we haven't realized this electric propulsion yet? So currently, I should say one of the major advantages of the combustion engine, which is if you are looking at the road transport, the combustion engine is like 99% today, and the rest is like electric cars. So this one is a major reason because it's cheap. Because it's cheap is mainly because it has been developed for over 100 years, right? The technology already matured and the size of the or the volume of the production already up, so it's relatively cheap. Electric propulsion or electric cars, maybe we should be more specific. When we're talking about electric propulsion, there are two types. One is a battery electric vehicle, and the other is a fuel cell electric vehicle, right? For both processes, they convert the chemical to electrical and then to the to mechanical. So they are still expensive, and particularly for the fuel cell. Battery actually, their price actually gone down quite a bit in the past 5 years. Actually, it's the price drop at a rate is higher than people initially thought. So when the volume goes up, the production volume goes up, the price drop very quickly. So the cost is one of the major advantage or strengths for the combustion engine, even though it's getting smaller and smaller. And the other advantage actually is more inherent. That's what we call the power density, or higher power density. So in other words, a smaller combustion engine can deliver a large amount of power, and if you want to achieve that same power, you need a large battery pack or large fuel cell pack in order to achieve that. And also, slightly different concept is combustion engine also have higher energy density. So that is saying that if you have one tank of fuel, right, which is for a typical size of a car, you will have a 60 liter or 50 liter of tank. It can carry you go to 300 to 400 kilometers, right? But for the battery, currently its energy density is still low. You have something called the range anxiety. So if you drive, if the range is like 150 kilometers, then after 100, you really become worried. Not only you are concerning whether you can get there, also if you want to find a place to charge, you want to, the charge station is not available everywhere at the moment yet, right? And also the time for the recharging is still quite slow. So these are the, I would say, technologically, still the advantage by the combustion engines. All right, so that's the comparison between this new technology. And in terms of the combustion engine, can be generally divided into two types. An idea in terms of how can we classify a combustion engine into two types: external and internal. Yep. External combustion engine and internal, right? So which one is more common? Internal combustion engine, right? Internal combustion engine, also called ICE, as its short name. So they are both using a combustion process, but the combustion happens in different way in terms of to provide the power or to provide the propulsion. So for external combustion engine, so that's a device where, for example, if we have a cylinder piston setup, external combustion engine is where the combustion happening outside this cylinder piston setup. So you have the combustion happening over there to heat up the working fluid inside this chamber, and then when this working fluid receives the heat, then it will expand and push the piston to do work, right? This process is not very efficient, or I shouldn't say not very efficient, not very fast, because later on when we learn the heat transfer, this is basically the gas transfer heat to another gas. So this process, in terms of heat transfer rate, is inherently slow. And the two gases are separated by a wall. You have to rely on the convection to the wall and the wall conduction, then the convection to the gas inside. So this process is limited by heat transfer, is inherently slow. But that's the first, actually the first type of combustion engine that has been invented. So one example I have here, a few examples actually. All right, so I leave one for the note. All right, that's it. So if you ever go to the Belgrave and take the train, so this is a steam train which is currently running in eastern suburb of Melbourne. So the powered by steam engine. So steam engine is the one type of external combustion engine where you have the combustion happening outside the cylinder not necessarily a cylinder, you combustion to heat up the steam, to produce the steam, and the steam, when it's heated up, it got the pressure, temperature, and can push things and to do work, to drive a train. So that's one type. And another one actually is, this is a short video. So this is an example of the, there's no sound. Okay, it doesn't really need a sound. So this is a good demonstration of an external combustion engine where you can see the combustion or the flame is indeed happening outside the engine. And this one is powered by, I think the fuel should be the alcohol type of fuel. So when it's burned, it heats up this side of the wall, and when it's being heated up, the gas inside will expand to push the cylinders and to do the work. So that's actually a good demonstration that the things combustion is really happening outside the working fluid, where the working fluid stays. So let me. All right. So for the external combustion engine, where the working fluid is not participate in combustion. And for the given example, actually that's running on the Stirling cycle. So what happens is you have the combustion happening here to heat up the gas and push the piston to do work. And when the piston being pushed away to an end, you can see there is quite a bit of fin type of structure here. Right? So that is to enhance the heat transfer. And when the gas is getting to there, because of the fin structure, it loses heat. The temperature goes down. And when the temperature goes down, the pressure goes down. Right? Then the piston, lower pressure, the piston will move from the this side to that side, to going back. Then when they reach the other side, it's hot, then being pushed again. So this is back and forth process to drive this Stirling engine. So in terms of the performance or general structure of the external combustion engine, I should say there are major features, particularly in comparison with the internal combustion engine. They're generally pretty large in terms of the size, but it can run at a pretty, if you design it properly, it can run at a pretty efficient in terms of the energy conversion. So it's a higher efficiency. And I should say there is a downside. Downside is because the heat transfer rate limiting how much power it can produce. Generally, this type of engine has a large size and has a lower power density. So I should say in comparison with the internal combustion engine, right? Compare with the other type of, like the electric propulsion, that still can be high power density. So it has a lower power density compared to the internal combustion engine, right? So if you design it right, they can have higher efficiency, and because this type of engine does not have any valves, so when we have an internal combustion engine, we need valves to allowing gas to in and out. Does not have valves and have minimum amount of moving parts, so this type of engine can running more smooth. Okay. And as a result, it can be quieter. So it finds certain application which to take advantage of these specific features. That's the one showing here. So Stirling engine has been used in submarine. And the reason for that is for submarine, the power density is not a big concern. So if you consider the three types of transport: air, road, and water. So they have a different requirement in terms of power density or in terms of the power to weight ratio, right? For the air transport, they have the highest requirement, or they require the engine to have the highest power to weight ratio in order, because directly working against the gravity, right? But for water transport or marine transport, they have least requirement because you have the water, have buoyancy to support you to the first hand. And for the submarine application, actually need a weight, otherwise it will be stay on surface all the time. You need a weight to going below the water surface. So this type of submarine using the so-called Stirling engine, which is the same cycle driving the small car we just saw a minute ago. So they are using the feature where the engine is very quiet, and that's the key design requirement for submarine, right? Because you don't want to produce a lot of acoustic signature to attract your enemy. So that's the one of the place where the external combustion engine still find a pretty good application. All right, so that's the external combustion engine. Say Stirling engine is used in the submarine application. So that's external combustion engine. So if we're looking at the internal combustion engine, certainly by its name, it's you have the combustion, have the piston cylinder setup. You have the combustion happening inside the cylinder. And the working fluid refers to the fluid to directly do the work for the cycle, right? The working fluid is part of the combustion process. So that's the major difference. The external combustion engine does not, the working fluid is not participated in the combustion. Internal combustion engine is again, it's the most common one used today. So they have higher power density. So a typical example, including the common one that we see for the road transport, gasoline engine. Gasoline engine is named by the fuel it used, or we can call it petrol engine. So this combustion happening there actually is using the so-called spark ignition process. You're using a spark plug to ignite the charge to start the combustion process. And there's another type, which is a diesel engine. Diesel engine is using a different type of combustion process called a compression ignition. So diesel engine, there you do not have spark. You just compress the air, and when the air is being compressed to the high temperature, you inject the fuel. Because the temperature is so high, when the fuel being injected, it will auto-ignite by itself. So that's called a compression ignition process. So these two types of engine basically dominate the road transport. And they're also being used for other applications, like for the power generation. So they are running on a process which is called either in terms of the Otto cycle or in terms of the diesel cycle. So here I show you an example in terms of four-stroke reciprocating engine working principle. So if it's supposed to play the animation. All right. So this is a four-stroke process, which is basically describe what happens in a spark engine, in a gasoline engine, or in a diesel engine. So the things there are happening in cycles, or in a periodical manner, or in the reciprocating manner. So you have several steps to complete a cycle. Then after these 4 steps, the things will return to the step 1, then going on and on. So you're involving four-stroke engine involving 4 steps. Intake, where the fresh charge to come in, and then you compress it. Then when the combustion happens, it will produce power to push the things push the piston down, and the last step to get the combustion product out of the cylinder for the next cycle to happen. So the process happening here is not continuous, even though the engine can running at a very high speed in terms of the rotation, but the actual process is not happening continuously. It happens in a so-called reciprocating way. So this engine being called a reciprocating engines. So the combustion happens in a periodical manner, right? So that's different from the engine we're going to discuss in this chapter, which is gas turbines. That's the third type of internal combustion engine that is commonly used. In a gas turbine engine, the process happening is indeed or truly continuous. You have the air continuous coming, passing through the compressor, getting into the combustion chamber, and the fuel is being continuously injected into the combustion chamber. Then the combustion product leaving the combustion chamber to drive the turbine and to produce either shaft work or the thrust. So gas turbine is a continuous process. The gasoline engine and diesel engine are not. So this is a continuous process. All right. So if we compare these two types of engines, if we classify the gasoline engine and diesel engine as reciprocating engine and the gas turbine as the other type, if we compare them, they feature different, again, the advantages and the weaknesses. So that's actually determining why they're being used for different applications. By convention, that's something actually you may want to know. When we're talking about internal combustion engine, often that only refers to this gasoline and diesel engine. So even though by definition gas turbine is also an internal combustion engine, but if you either reading reading news or reading literature, people generally refers to internal combustion engine as this reciprocating type of engine, and the gas turbine being refers separately, right? So that's just something for your information. So if we compare gas turbine versus gasoline and diesel engine, gas turbine has certain advantages. So one of the advantage, it has higher power density. So that refers to the gas turbine. So even compared to the among the different type of internal combustion engines, a gas turbine has the highest power density. So which means a small engine can produce a lot of power as the output, right? Another advantage is if you consider the way a gas turbine works, it has a compressor, compress air, then the air with the fuel being injected to burn, then to drive a turbine. So the movement or the part, how the parts are moved is mainly rotational, right? When you have in fact, the turbine and the compressor, they are co-shafted, so they are on the same shaft. So they are turning together. So rotation is inherently stable. Compared to in a piston engine or reciprocating engine, the piston is going up and down, and it relies on a crankshaft at the bottom to transfer that linear movement to rotation movement at the wheels. So because of that, the gas turbine can run with less vibration and also can run more smoothly. It's not necessarily saying it will have less noise, but it can run with less vibration. And because of everything is rotating, gas turbine typically can run at a higher speed in terms of, we call it RPM, revolution per minute. An aircraft engine can run at a higher RPM than a car engine. So that's the strengths. It should be the two major strengths for the gas turbine. So the downside of the gas turbine, the first is it's expensive. The compressor and the turbine, later on we will watch a video to see the inside of this device. So there are many layer of blades being put together, and they need to be put together very accurately. So it requires high precision machining. So that makes the cost of a gas turbine typically more expensive than a diesel engine or gasoline engine for the same output. And another downside is, in terms of engine efficiency, it's less efficient. Less efficient by the GT cycle only. So if you're running a GT cycle, for example, the Brayton cycle we are going to discuss later today, the efficiency is lower compared to a diesel cycle. We briefly mentioned diesel cycle is more efficient than the Otto cycle, which is for the gasoline engine to operate. So it's more expensive and less efficient. Another downside is a gas turbine have a poor dynamic response. So if you operate a gas turbine, you do not want to change the load very often. You want the engine will running very smoothly if you running at a constant load. So if an aircraft is cruising, running at a constant load, constant power output, that condition the engine is working at its best condition, and is unlikely to cause problem. But if you have application, you have to change the load very frequently, or you have to stop the engine and restart the engine very frequently, then that's not the case for the gas turbine. All right, so that's the reason that in the road transport, right, if you're driving a car, particularly in the city, you have a lot of occasions that you have to stop and go, and in certain cases you want to accelerate or quickly decelerate. So in that cases, you don't want to use the gas turbine. You want to use the piston engine for that purpose. All right, so that's the comparison between these two, and that actually determines the application of the gas turbine. So that's leading to the discussion we are going to have. So gas turbine applications. There are two major types. One is a question for you. Where the gas turbine engine is being aircraft. Yeah, so that's a aircraft propulsion. So if I have the slides up. So this is the Airbus 380. That is powered by a 4 huge-sized Rolls-Royce turbofan engine. And because of the high power to weight ratio, the aircraft, so today, or modern aviation is almost all the craft is powered by the gas turbine engine. So that's called a jet engine, or if you're using a more common term or more non-scientific term. So you still, for certain recreational purpose, you can still have the piston engine in your aircraft, but that's not for the commercial flight. It's certainly not for the military flight. So for predominant application, you're using the gas turbine in the aviation. So that's one common common application for the gas turbine, and less common, or if you have some interest to read certain literatures, you'll find that the gas turbine is also used for the marine, or maybe I should say just marine transport. So this is one example. Again, it's because of the high power to weight ratio. For the military application, you want the warship to be as light as possible, so that and it can produce a lot of power, so that the ship can run at a higher speed, right? So this is one case that there is 4 GE engines being installed on this Arleigh Burke class of destroyer, and to prepare this warship, and actually each produce 20 megawatts of power. So if you have idea in terms of a car power, a car engine, 4-cylinder or 6-cylinder, typically give you a power of 0.1 megawatts. So this one is like 800 of a car engine put together. All right, so that's one application. That's for the warship. I should say for the typical application, typical marine transport, you do not necessarily using the gas turbine. In most cases, you're still using the diesel engine for the marine transport. Another specialty application, which is really special, is the road transport. So this is a manned battle tank. This is probably the only application where the gas turbine is being used for the road vehicles. So in this case, it is using 1 megawatts of Honeywell gas turbine to power this Abrams tank. And in most other tanks, actually, they are still using the diesel engine. So again, it's because of the high power to weight ratio. So you have a small engine can produce a lot of power, which is particularly useful for the military application. All right, so these three basically, they are for the transport purpose, right? The other major category of the application of gas turbine is what? Power generation, yeah. So in this case, consider that a piston engine you can build with very large size, but there is a limit. So if you build the piston engine over a certain limit, then it's become not technically viable. But a gas turbine can be built a very large size. And when you build something large and produce something large, the cost is, on average, actually is going down. So that's the reason that you're using a gas turbine for the power generation. And another reason is if you're running on the gas turbine cycle itself, that's, as we said, is not as efficient as a diesel engine or diesel cycle. But if you combine the gas turbine cycle with some other cycles, the process actually can be quite efficient. So that's the, actually I should say that the most efficient power cycle to date is something called combined cycle, which you combine the gas turbine cycle with the steam turbine cycle, then it gives you the highest efficiency, certainly higher than a diesel cycle. Right? So that's the things we are going to discuss in more detail in this chapter. All right, so finally we get back to the technical part of this chapter. So let's discuss the Brayton cycle, which is a cycle using a gas turbine. For the power generation. So when a gas turbine is being used for the power generation, the useful output is the shaft work. Later on, we are going to discuss when gas turbine is used for the propulsion. So in that case, the useful output is not shaft work, but thrust. So you produce high velocity gas, which is to propel the aircraft. So that's different in terms of the output. So here the shaft work, to increase the amount of shaft work as output, that's the target here. I assume you all have learned this before, so I go through this basic cycle quickly, and we are going to discuss how to improve this basic cycle. That should be the next lecture. But let's go through this basic Brayton cycle. Brayton cycle, or a typical gas turbine cycle, you have working fluid coming in, right? Getting into a compressor, and after compression, you have this working fluid into a combustor, and the combustor then will output high temperature, high pressure working fluid. Then you're going into the turbine, and the turbine is to deliver useful work. Then the working fluid leave the turbine. So as I said, the compressor and the turbine, they are coaxial. So the turbine, basically the compressor is driven by the turbine. And in this process, you have the, if we call this one state 1, 2, 3, and 4. At the compressor, you have the work being input into the system. And then at the combustor, you have the heat being added into the system. And the turbine, you have work being output from the system. And to close the loop as a cycle, in fact, we consider the exhaust gas being cooled by this ambient then coming back to the inlet, even though in reality you just dump this exhaust and bring in the fresh air in. But in order to complete a cycle, we consider the gas coming back, and in this process you will have some heat output to the surroundings. Right, so that's pretty straightforward, 4 steps. The step 1 to 2, if I draw the TS diagram, if I draw the TS diagram, one to two going through the compressor, we consider that process is isentropic. Compressor is a device we consider in the ideal cycle that should be an isentropic process, right? So that's isentropic compression. So on the TS diagram, for isentropic process, we will have what type of, how do we draw this? A vertical line, yep. 2, 2. Then the 2 to 3 is where the external heat is being added to the system. So this process is a constant pressure. So you consider the gas passing through the compressor and picking up the heat along the way. So that's a constant pressure or isobaric heat addition. So for isobaric or constant pressure on a TS diagram, we would have we don't have a straight line anymore. We have a curved line get to the state 3. All right. So that's the heat being added. So this is work input, heat in, or maybe I call this compressor work, W, of the work of the compressor. And then the state 3 to 4 going through the turbine. Again, in ideal cycle, it will be considered as isentropic. Expansion. Right. Then we have another vertical line coming down to state 4 to deliver the turbine work. And the last step is isobaric heat rejection. All right. So you want to recognize that the constant pressure line on a TS diagram corresponding to 2 curves. So this cycle actually is just working between 2 pressure, high pressure and low pressure. So each of this line and this line corresponding to a constant pressure. So compressor is a device to bring the pressure up, and turbine is a device to bring the pressure down. And you're just working between 2 constant pressures there. All right. So we can quickly go through how to calculate each of these energy terms. So that's the, then we can figure out how to calculate the efficiency of a basic Brayton cycle. So if we have the, if we want to calculate the process 1 to 2, we are dealing with ideal cycle. I should briefly define the ideal cycle. Ideal cycle is a reversible cycle, and without any loss. There's no temperature loss, no heat loss, no pressure loss, which means no friction. And this process is only having air. So air is only working fluid. So the fuel, even fuel is burned in the reality to heat up the temperature. We consider the air is only working fluid and just the heat being added from the outside to the system, right? And also air has the constant properties. Its Cp does not change with respect to temperature. All right. So if that's the case, from 1 to 2, we can figure out how much is the compressor work. We have the first law. Q minus H, Q minus W equals to delta what? U? H, yeah. Why? We're dealing with, what type of system we're dealing with? An open system. There is no enclosure for the air in and the air out, right? The air continuously coming, continuously going out. This is a flowing system. This is an open system. So we should be using the first law in terms of it's called the steady flow energy equation, delta H. So if I have H2 minus H1, right? So this process is isentropic. Isentropic, by definition, is an adiabatic process. I probably haven't mentioned this. In our discussion here, when we're talking about isentropic process, we consider that the process is reversible and adiabatic. So let me clear here. So isentropic because in most cases, for the psychoanalysis, we're dealing with ideal case. If you just follow the isentropic, which is saying there's no change in terms of the entropy, it could achieve in a non-ideal way as long as the initial and end are the same, has the same entropy, right? But here we're dealing with more of the ideal case. So if you have a reversible adiabatic process, you will satisfy the isentropic requirement. So if we put with the reversible process, we can write heat transfer equals to T ds. Reversible process, all right? It's only, this equal sign only valid when you have a reversible process. And if you have adiabatic process, which means this small change in the heat transfer, actually that's 0. Adiabatic, right? There's no heat transfer whatsoever. So then you would have the ds equals to 0. So in the discussion here, we always refers to the isentropic as an adiabatic process. All right, so now we can continue from here. So because it's isentropic, then this Q goes to 0, and the work minus work 1 to 2 equals to Cp T2 minus T1. And this is a negative work because work is down from the surroundings to the system. When we're dealing with each of these terms, we're only dealing with their absolute value. So the compressor work and the turbine work, we're only dealing with their absolute value. So we call WC equals to the absolute value of from step 1 to 2, then equals to Cp T2 minus T1. All right. How the T1 is a starting point, typically is given. How do we know the T2?